Hello, my name is Gu Xie. I work at Virginia Tech Libraries as a professor and the Chief Strategy Officer. The title of my talk is Choosing Archival Format by Machine Consumption Efficiency. This talk sums up major findings of our IMLS-funded research project, developing library cyber infrastructure strategy for big data sharing and reuse. The central thesis of my talk can be summed up as follows. To preserve big data, we must carefully choose an efficient archival format for reuse. This typically leads to a binary data format that is optimized for efficient processing in big data systems. An efficient data format is usually not for human consumption, therefore eliminates all textual data formats from XML, JSON to CSV. Although counterintuitive, the performance gain of the efficient archival format can be a life and death decision for an archival system. Why? Because with the rapid growth of archival data size, the use cases are changing, and poor performance can render traditional archival systems unusable. Now let's dive into more details. Today, big data preservation is no longer mere buzzwords in libraries and archives. The flagship scholarship repositories have grown significantly in sizes in the past decades. Moreover, not just the big science projects, but small science teams and regular guys like you and me can now easily collect tens to hundreds of terabytes of research data that worth preserving and reusing. The growth of the data size not only exceeds the storage capacity of our laptops and desktops, the more challenging aspect is that even if we can beef up of our local storage, we usually don't have sufficient processing power to make sense of them. This leads to a paradigm shift in archival systems from a repository-centric view to a data-centric view. Let us look at the OAIS model. Here, consumers gain access to the archives through an access module that essentially does two things. First, it responds to user queries, and second, it delivers dissemination information package or DIP. A traditional repository takes a narrower interpretation of this model that will only respond to prescribed simple queries like those against the predetermined metadata. If you want answers beyond those simple queries, sorry, here's the DIP. Download and go figure it out by yourself. A traditional repository works fine if the size of the DIP is within the end user's data processing capacity. But in big data scenarios, this is usually not the case. For example, only in September 2020, Common Crawl has collected 3.45 billion web pages. The whole data set is available for downloads, but who can easily spin up a cluster to query 3.45 billion web pages? Not me. It is therefore necessary to shift to a data-centric view where the preservation system not only need to provide archival storage and basic query facilities, but also user programmable computational resources to manipulate archival data in place. Along this new paradigm, Common Crawl hosted their datasets on the Amazon cloud, which provides both the computational and the storage capabilities for consumers to conduct customized query beyond these simple metadata queries. Now we can spin up virtual machines and write our own code to answer queries like how many times 9/11 is mentioned between September 10th, 6 a.m. to September 12th, 6 p.m. by web pages in the ac.uk domain. Such queries have been impossible for traditional repositories. Similarly, although HTRC does not provide DIP downloads, it does provide the computational infrastructure to run customized queries against the copyrighted bookscan corpus. Now that we have some basic understanding on big data preservation systems, let us turn to the data format. Why is data format important? Because we found out through experiments, even equipped with similar big data processing systems, the same query could take 40 seconds to complete if the data are preserved in one format, but would take almost 4,000 seconds to complete if archived in a different format. Our research project was initially intended to benchmark different big data archival and processing systems and optimize their performance by adjusting settings and configurations. To our surprise, however, stunning performance gain can be achieved not by changing the system settings, but by changing archival data formats. And the culprit is usually the friendly human-readable textual formats, which include but are not limited to XML, JSON, and CSV. Why? I'll show you a few examples. Look at this timestamp. If encoded in text string, here is how it's translated into binary and stored in a computer. But if the same timestamp is encoded in integer, which signifies the number of seconds from an epoch time, it's stored in this integer, which translates into this binary form, which is much shorter. The size of the storage is not only the issue. A computer can easily compare two integers and knows which is larger, therefore, which is a later timestamp. It cannot easily tell which string signifies a later timestamp unless the string is converted into integer. Not only do we waste storage space, but also waste computational cycles to convert human-readable text to machine-understandable integer. Here's another example. In the left free text, try to imagine how a computer finds the fourth sentence in the second paragraph. Also, on the right, there's a table. Try to imagine how a computer finds the fourth column of the second row in this table. Which is easier for a computer? That's obvious, isn't it? So to summarize, why data format is important? Because data format stipulates how information is encoded, organized, and stored. Human-readable formats can be difficult for a computer to make sense, and they typically take more storage and computer cycles to query. Although the computer becomes faster and storage becomes cheaper, by definition, these growths are outpaced by the deluge of big data. Small performance savings here and there, therefore, can translate into major performance gains. For example, from 4,000 seconds to 40 seconds. To understand why data format makes such a big difference, it is worth reviewing the rationale behind modern big data systems. First, although these systems can quickly process large amounts of data, they assume that data are comprised of structurally repetitive records with very low interdependency. Under this assumption, large data sets can be efficiently partitioned and replicated and processed in a scalable manner on commodity computers interconnected only by the network. Nevertheless, basic physics law still applies here. For example, network transmit is always much slower than local data access, and the spinning disk is much slower than memory. Scanning large contiguous data blocks on disk is also more efficient than combining many random access together. Modern big data systems respect these constraints and work coherently to leverage these constraints. That's why we have data replication systems like Hadoop file system, in-memory processing system like Spark, and a columnar database like HBase. All this means that these systems rely heavily on the data locality, space efficiency, and caching to work properly. If data are not formatted to this rationale, then the big data system cannot properly leverage their built-in mechanism to efficiently use the computing resources, therefore the low performance. So to better understand the logic behind our focus on data format, allow me to make an analogy. Compare the difference between a modern supply chain and my home organizing system. In my home, I much prefer to organize all my stuff as in these lower pictures. I can easily browse my belongings and find the things I want this way. However, the human scale is not necessarily the most efficient one if my stuff grows. The modern supply chain components such as container port The industrial warehouse and the barcode and QR code, they're not designed for human-friendly. I can easily understand the barcode and the QR code or move a container. That's meant to be handled by specialized machine. Indeed, modern container port reportedly employs only a handful of workers. Everything else is automated for machines. But if I insist everything is labeled in plain English for my convenience, the modern supply chain could have to be slowed down significantly. For the same reason, we should not preserve archival data in a format that do not take advantage of the efficiency requirements of modern big data systems. That's like trying to move my home closet and pantry across the Pacific without packing them into packages and then use the ship container. Ultimately, the efficient data format would be not only awkward, but also very wasteful. So it turns out that we're also not the only ones concerned with data formats and performance. In recent years, many widely adopted data formats have been challenged for their efficiency and performance when growing larger. The list includes FITS, that's for astronomical data, HDF5, which is used widely in science and engineering, and the two more widely adopted JSON and CSV data format. Take JSON as an example. It has been shown that big data systems process JSON data spend more than 80% of the time on data parsing and loading. Use the supply chain analogy. This equals to spend 80% of the time packing my closet and pantry to fit stuff in shipping container and then spend less than 20% of the time to ship them. If this is the case, why don't we just store all our belongings in shipping containers to cut the cost? This is indeed our proposal. But what if we need our shirts and cooking utensils handy without having to unpack them from the shipping containers? It turns out this is not the case for archives. Most of the archival data are the so-called code data. They are only accessed very infrequently. Therefore, they live in the preservation systems that are accessed much less frequently than those hot data. For example, those used for Google search. Now we quantify the performance gains of more efficient data format using web archives as example. We extract the 3 typical web archive and reuse workload, approximately mapped to data filtering, analysis, and aggregation. We then compare the performance of querying data formatted in a WARC or work with CDX index with the same data reformatted in Parquet and Avro. WARC is an ISO standard which is widely used by web archives. However, it is a textual format. On the other hand, both Parquet and Avro format are open data format. Parquet originated from the Google Dremel project, which defines a highly efficient algorithm to flatten nested data structures such as XML and JSON into columnar storage. The so-called columnar storage organizes the data in a way that the values of the same column of all records are stored together. Therefore, it's much easier to do columnar queries. Avro, on the other hand, is a route store format. Big data systems have been designed to take advantage of these predictable data structure and shortcuts afforded by both the columnar and row stores. So both Parquet and Avro are binary formats, meaning many primitive data types have been defined such as those data can be stored in an efficient machine native way, analogous to using barcode or QR code in modern supply chain. The repeated parsing, packing, and unpacking is therefore eliminated. In our benchmark, we're able to achieve performance gain in 1 to 2 orders of magnitude faster simply by reformatting textual data formats. Our results are by no means surprising. As early as 2013, a group at UC Berkeley and Cloudera has already achieved a 28 times speed up by reformatting genome data from SAM-BAM to a combine of Parquet and Avro. Therefore, the reformatting basically rearranged the data in a way that big data systems can leverage to achieve much higher performance. This concludes my talk. This project, here's the acknowledgement. The project is made possible by NRMS and NSF grants. Thank you very much.